short credit for the quiz then.
Yeah, I thought you already sent it to me. You already sent me a picture
I
of
did?
it.
Oh,
Yeah.
okay. Well, here.
You can keep it.
Okay.
I already wrote you about it, I think. So you're all set. Thank you. Thank you for doing that. Okay, so we'll wait for some folks at home to get online here. Make sure they can see the board. And life is good. Okay, you guys are a little close. I probably got to move one of you back. So Keanu, just move back so we're not three there. That's just too close. So we'll move you back there to one. So, thank you. Okay. All right. Yeah, where we left off last time was talking about some kinetic energy diagrams. Let's review one because I know you did this from home and it's not that easy to see everything from home. I don't need my whiteboard markers because I got a chalkboard here. And let's see if I got some folks. I do. There's UCN checking in. Hello, UCN. And there's Mick. Hello, Mick. Thanks for joining us. I'll try and get it so you can see everything good today. I'm going to move this down to there. And, ooh, it didn't like that. I hope you're still there. And I got Tilly. Hello, Tilly. Super. Okay, so let's review. We said we got molecules have a certain amount of kinetic energy. We're going to put that here on the x-axis. What was kinetic energy? Just in your own words. Kinetic energy, Emil? Good, energy of movement. So if it's moving, it's got kinetic energy. Good. And on this side, we have number of molecules. Okay, so then I just drew something that looked like this. And we said, okay, this is a high amount of kinetic energy. This would be low. What do you suppose I could say about the molecules out here at this end? How might they be looking different than the ones over here? How might these guys look if I could see them? So think of what Emil said. It's the amount of movement, kinetic energy. How might these guys look different at this end? Keanu? Yeah. What could be, what do you mean by more? Moving what? Yeah? Okay. Moving how? Faster. Faster. So these guys are moving faster. Where are the ones moving slower? The ones moving slower. We're all in different seats and with masks on. Aaron? Bottom left. Bottom left. Good. So these guys are moving slower. So I got a lot moving in the middle. Okay. What if I... And Julius is there too. Good. Thank you, Julius. Here's a question for folks at home and for here. What if I heat the molecules up? Let's say orange is going to be a hotter temperature. How will my graph change? What if I heat them up? So I want a higher temperature. How will my graph change? Got a couple guesses? What could happen here? You're going to heat them up. All right, Lisa, what do you think?
Like this high part is like moving more towards the right.
Okay.
Like also it's not that high, it's a bit
Okay.
low.
Yeah. So importantly, it's going to move to the right. So I've got more of them that are faster. And look at this. I got less of them that are slower. So remember, this is number of molecules. I know this is pretty abstract. Okay, that's why we're practicing a lot because it's not easy. I understand that. So I got less slow molecules. I got more faster ones with high kinetic energy. That's what that means. They're moving a lot faster over here. All right? Let's say, so I'm going to say that color equals hotter. If hotter. Let's say blue is going to be colder. There.
Ones that have more molecules and less kinetic energy.
Not more molecules. Let's say it's still the same box of molecules. But if they have less kinetic energy, how will that change the bump, David? Let's say we start with
that would make it like extra 4 and like go to the left.
To the left. Okay, yeah. And it ends up being higher as well.
Yeah, that's what I meant by
Okay, all right. So it's almost like this. It's the same total amount, but they're squeezed together more because there's less different temperatures they can be. So they're all sort of stuck in this really just a few different temperatures they could be. Yeah, Yulia said that as well. Thank you. And Tilly said that as well for the hot one. They had to move it to the right, and I bet they said move to the left for the cool one. Sorry, there's a lag. I don't get your answers right away, but appreciate it, Julius and Tilly. Good. I know you guys were home. Ask me questions. Try and put it into words. Anything you want to ask me about this. We're going to practice a little more with this too. Okay. Lisa?
I don't know, like, we also do like the activation energy.
Exactly.
I think I need a little more explanation.
Good. All right. So here we go. Activation energy. Here come two molecules. They're just floating in the air. Ready? Oh, they touched, but they didn't really do anything. They collided, but it was pretty wimpy, wasn't it? What do you suppose has to happen for them to react? What do they got to do, Frederica, these two molecules? They can't just bump into each other. Emelina?
Move faster,
Yeah, what about how they hit?
harder.
Now they're going to react. To hit hard enough to react, that's really what chemistry is about. I know you don't think of chemistry as being some kind of violent thing, but if you could see the little particles, they're hitting each other all the time in the air. And our air doesn't react much, luckily. But some things do. Some things do. And to actually get to reacting hard enough to go, they've got to hit pretty hard. Case in point. Here's my imaginary candle, right? Imagine I got a candle here. Candle wax can burn, right? But why isn't it burning? What do I got to do? What do I got to do? Yo. Yeah. Why? What do you suppose the flame does? What does the flame do to those molecules? Go.
It makes them go really hard enough to react.
Exactly. That hard enough to react is the phrase that Lisa's referring to, activation energy. If I don't have the match, then they're still hitting, but it's not hard enough to do anything. They're not going so they'll actually react and make a fire, okay, make a flame on my candle. But if I put a match there, suddenly the wax particles and the oxygen in the air, bam, 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 boom, and they start to react, and then I get a flame, okay? So that energy is called the activation energy. And it really is enough kinetic energy. So energy of movement. So particles. So atoms or molecules. Okay, I'm just going to call them particles. Get hard enough to react. If you don't like the word hit, we often say collide. Well, what that means is I can often put a line on a diagram. And I'm going to do that in a second once we catch up. And I'm going to do a new diagram because I don't want this to be quite so busy. Questions before I go on, or from folks at home? I got a Tully now as well. Thank you, Tully, for joining us there. Okay. We all right? Okay, let's do a new kinetic energy diagram. I'm just going to erase the whole thing. Okay, let's say that, and you're not going to know this because you don't have the data, you don't have the numbers, but let's say I know that the line right there is the line that we put for the activation energy for a certain reaction. If that's the activation energy, then on which side will be the molecules that are hitting hard enough to react? On which side of that line? Emil?
On the right.
On the right side is correct. So I'm going to mark that and just say all of these suckers, bam, they got enough kinetic energy, right? They got high kinetic energy. These can react. These over here, they're going to what, Matthew?
Not react.
Yeah, because how are they physically? They're
not,
to what?
going as fast, so they're not colliding.
Exactly. They're not colliding as much and they're not colliding as hard. So if these guys are going like this, boop, right? Boop, I get little baby collisions. That's not enough, man. I need, like we were saying over here, I need to get a match or something to get these guys going. And I need only the most energetic ones are going to hit hard enough to collide and make something new happen. Okay. Last time we talked about, and I think we did it where you could see me too, a high explosive called nitroglycerin. It's a liquid. And if it's at room temperature, you got to be really careful with it. Because at room temperature, nitroglycerin is pretty unstable. Any little movement can give it enough kinetic energy for what to happen. Emelina? Exactly. So how do you suppose the activation energy is for nitroglycerin compared to this line? Where might be the line for nitroglycerin on this? Frederica? Further to the left. So, oh, maybe I've got a line here that's like activation energy. I'm going to abbreviate it now for exploding nitroglycerin, okay? Something I don't recommend. Oh man, be careful with it. Be careful with it. I would have lots of molecules reacting, wouldn't I? All of these would react. Whoa, that would be a lot. So what did we say that people did with nitroglycerin to make it so it doesn't react? Keanu? Yeah. What will that do to this bump, this white bump again, if I freeze them? Keanu? You got it. So let's say they do that. And now, is the nitroglycerin safe? Why? Who can say it in words? If these are my molecules now, so this means I got colder, let's say nitroglycerin compounds. Nitroglycerin particles. Well, molecules, we might as well be clear about that. So why is it safe now? Emilena?
Because it's not over the activation energy, it doesn't pass the light, so it doesn't react at all.
Yeah. Tell me about the collisions. They'll still collide with each other, but what about the collisions? Keanu?
They move slower or they don't move at all because they're frozen.
Well, they're still moving if they're frozen. They only don't move at something called absolute zero. But let's say we're not there yet. But they're frozen. They can still move a little like this.
Yeah, so they can hit each other,
Yeah. They don't hit strong enough to do what?
make a reaction.
Exactly. So if they're all here, life is good. So sometimes, folks, sometimes you don't want a reaction. Sometimes you do. It depends, doesn't it? I don't want to blow my hand off, so I don't want a reaction here. I want to blow it in the mine where I want to use it to blow out rock. That's what they use nitroglycerin for. Questions, comments, Matthew?
How did they figure out that freezing it would keep it from exploding?
Somebody just had this idea. They were using it in Western North America for mining. They're trying to make actually, where was it? I take it back. It wasn't even out west, Matthew. I remember where it was. The first time they did this, how many of you been to New York City? Any of you been in New York City? A couple of you have? Okay, all right. There's a tunnel there. It's called like the Holland Tunnel. It goes under, I don't know what it goes under. I haven't spent much time in New York. But when they're in the middle of that tunnel, they're running out of money because they're like the progress was going pretty slow. And they said, well, we need to start blasting. So we're going to do that with nitroglycerin. But it was so unstable. They had a couple of wagons blow up and stuff. You know what I mean? So somebody just had the idea, what if we freeze it? They just tried it and it worked. That's before, it was before 1900, so it's before people understood a lot about atoms and molecules, you know what I mean? But they figured out, it was a good guess, Matthew, that if you cool it down, it doesn't react as much. So they would bring it to the site, frozen, and then they'd let it warm up, and then they'd use it in the mine to blow out the rock, the tunnel to blow out the rock. So it was just somebody's good idea. Go.
How did they activate it? When they put it in the rock, did they activate it with like a shook or with the lighting?
Well, they can't be anywhere near it, right? So can you guess what they did? David? Well, it's not, it looks like a pump, but it's not a pump. In fact, they didn't even really need to, I know they show that in the movies, but you don't really need a pump. What do you simply need?
You need like the rope that you light and then you run away.
Good. Exactly. The rope that you light is called a fuse. And it's more like a thin wire, almost like a really long match. We talked about a match earlier, right? So imagine I can light this fuse, and I know it's going to take about 20 seconds, okay? I've got it measured out. It's about a meter or whatever. I light it, and then I run like crazy to get away from that spot, right? And then it blows, hopefully when all the people are out of the tunnel safely.
So it blows up with heat.
Yep, because it needs some heat to make the molecules do what? Have more energy to get them past the activation energy line. And once they do that, in fact, once a few start blowing up, then, pardon me, once a few of them blow up, then I got plenty of energy there to do what? Make the other ones. So as soon as I start it, the whole thing goes. Then I got plenty of energy to make all of them blow up really quickly. Good. Question, Stephanie.
How much nitroglycerin do you need to blow up?
The pictures I've seen show a test tube about this big with maybe 50 milliliters of it, not that much. And that's enough to blow out a big section of rock like this.
How do you make it? Nitroglycerin.
I don't know. I've never made it.
Can we try?
I'm not sure I want to make it. And I'm not sure that would be the best 8th grade lab in case there's a mistake, you know? I don't really want to lose any of my students. So, no, I've never made any sort of explosives. I mean, I think you can, but I think you need probably a lot more lab gear than we have at this school, which is maybe a good thing, all right? Yeah, but they certainly, it can be made, and people did. It's generally used for, like I said, mining or blowing out rock in a tunnel or something, okay? Good. I think we're ready. So what I want to do now, as something new, is I want to give you 4 diagrams, 4 of these diagrams, okay? And I'm going to ask you a couple questions about them. They're all going to be kinetic energy diagrams. I'm going to try and do it so folks on the board can see all 4. I'll start right in there. I'm going to label them A, B, C, D. Yeah, they can see those too. Okay, so now, and they're all going to be the same. I'm going to put the label here, but it's all the same. Kinetic energy, number of molecules, okay? Or number of particles, or whatever you want to say. Okay, so. Okay, then I'm going to put some lines in each one, all right? Okay, so I'm going to do. Okay, so the blue line, folks at home, and I should have done a different color, but I hope you can see it. That's going to be the activation energy for each reaction. Okay, so 1, put in order. Hottest to coldest molecules. 2, put in order. Fastest to slowest reaction. Because part of our unit we're still on is rate of reaction. That's why this is coming into play, all these diagrams. Okay, so folks at home and here, I'm going to give you time to write all those and then take your guesses. I'll come around if there's something you want to ask me about them. But each of them has a distribution of molecules and an activation energy line. So write them and then really think about it.
Everything to the right of the activation energy line is basically where
Yeah, that's right. I'm gonna give you guys a hint. Based on what Coco said, I'm gonna give you a little hint here. Okay, write down your guesses. So, which one is coldest, fastest, whatever, hottest to coldest. So, A, B, C, D, D, C, B, A, or, whatever, however it is, and some are fastest and slowest. So take a guess for each set. Good, who's got a guess? Each guess now. Write down your guess, please. All right. No, it's the way the molecules are arranged on the diagram. Which molecules show the hottest conditions? Okay. Everybody got some guesses? Looks like. All right. How about hottest to coldest? David, which one do you think's the hottest?
Oh, the hardest?
Yeah.
D.
D. Want to give me the rest of your order? What'd you say?
D, then A, then C, and then D.
I like it. Why is D the hottest?
This is the most kinetic energy.
Yeah, they're way over at the right, a lot of kinetic energy. Why is B the coldest?
The least kinetic
Okay, so where are they? For B, okay, all right. So B, they're all at the left side, so the least kinetic energy. Okay. Let's go for the second one, fastest to slowest. All right.
I have B is the fastest because it has the most activation energy.
No, it doesn't have the most activation energy. It's got the most molecules where compared to that line.
They reaction.
Yeah.
So I have B, C, and D.
B,
D,
B,
A, C.
I think that's right. So let's think about why that is. So let's go back and I think Emelina's got it. Let's make sure we know why. This one. The activation energy is pretty low, but what about the molecules? Enrico.
Most molecules still are on the right side.
You got it. So most of the molecules are on the right side. They've got enough kinetic energy to react, don't they? Lots and lots and lots and lots of them do. Why is this one the slowest? C. Describe it for me. Why is that one the slowest? Coco.
Kind of an outside strength because it has the smallest amount of molecules that react.
Yeah. Because it's the smallest amount of molecules that have enough energy.
But I do not have kinetic energy.
You got it. So only these few out here are hitting hard enough to go ahead and react. The rest of them are not. These are all these are hitting wimpy, not enough to react. And maybe it's just because that's a lot of kinetic energy required. Over here, the one I did where Emelina had that as the most reactive, because the kinetic energy required, the activation energy is pretty low. So lots of molecules have that. So even with a wimpy hit, they're already reacting. Sometimes it doesn't take a lot of kinetic energy to react. Good. And Tully had the same thing. Way to go. For both. Good. Way to go. Way to go, Tully. Good. Okay. Questions about this? I'm going to just leave one of the diagrams. I'm going to leave C. And we kind of had this last time, but just as a review question, let's say this is the activation energy. For your body to fight a disease. Maybe it's a virus or a bacteria that's attacking your body. You got a cold, you got a flu, you got whatever. And we said last time, what does your body do sometimes to make the fight more effective? Do you remember? Yo? Heats up. We call that having a what? A fever. So if you've got a fever, let's see what that's going to do. Well, somebody tell me what's going to happen to the bump if you've got a fever. See that white bump? What's going to happen to that? You develop a fever. Lisa?
Gonna like move to the right. That's not what.
Okay. Let's do what Lisa said. She said it's moving to the right. Oh, well, what does that mean? Because you have a fever, what's happening with the energy to fight well, not the energy, that's staying here. What happens to the number of molecules that can fight the disease? The number of molecules fighting the disease? Emil? Increases by a lot. Look at it. Suddenly, all these molecules, whatever they are, white blood cells, whatever you've learned in biology, suddenly they're moving fast enough to fight the disease much better. So that would be with a fever. So your body does that same thing. Your body also increases your temperature to fight disease better. That's what it's doing. Good. And Tilly knew that too. She said it heats it up. Right? Oh, good. Questions from you? Okay, good. We have another type of diagram that I have to talk to you about. But first, I got to talk to you about this. Potential energy. You'll see what this has to do with chemical reactions. I promise it will. But first off, let's see if you had this in another course. What is potential energy? Or give me an example of something with kinetic energy. You had it, Coco?
So potential energy is basically energy that's waiting to happen, but it's still, it's basically like, imagine a football or something on a slope or something there, and it's someone's holding it here. If they let go, that's potential energy.
Good. In fact, I'm gonna just use something I got in front of me, a folder, and I'll say, there it is. My folder has potential energy because if I drop it, right, it's got the potential to go down. Now, if I have the folder on the floor, it doesn't have any potential energy because it can't go anywhere. Now it's got some. How could I make it have more? Matthew, what could I do?
Raise it higher.
Raise it higher. It's got more potential energy. Now, think of that word potential. It's got more potential to give off energy if I let it drop.
Something about,
Too late. I'll get it later. Okay. So, Matthew had me raise it up to make it, amen? Matthew had me raise it up to have more potential energy. What else could I change to make more potential energy? Could you guess? What else could I change?
halfway.
Yeah. So now instead of that, oh, let's say my object is all black. Oh, now I got even more potential energy. Okay. Potential energy is also really important in chemistry. So I'm thinking about how I want to do this at your level. Consider for a second. I like what you said first, also, Coco, that it's like energy that's waiting, because we often call it stored energy. Based on the position. Like I had it in one position, it had potential energy. I had it on the floor, it didn't have potential energy. I had it in one, it had potential. I raised it up, right? Suggestion from Matthew, it had more potential energy because of its position. Atoms and molecules work the same way. Sometimes they're in positions that are really pretty low energy. You and I talked about the periodic table, right? Can you guess a whole group that really has a very low potential energy? They just don't want to do much of anything. What group do you suppose has a low potential energy on the periodic table? Emily?
The noble gases.
The noble gases. They just don't react. They don't do much of anything. Their potential energy is low. It's not bad, they just don't really do much. Some of them have a very high potential energy. Some molecules have a very high potential energy. And this time, it's not because it's going to fall, but because it can give off energy. Okay, maybe you can guess what I'm talking about. What did we talk about earlier this hour that has a lot of potential energy, a lot of potential to give off energy? What chemical? Yeah. Nitroglycerin. So it's got a very high potential energy. Whew. We're going to make a diagram for exploding nitroglycerin. All righty? This time, we're going to have potential energy on the y-axis. Yes, I know you haven't done this before. Just bear with me, okay? And on the x-axis, we're going to have the stages of a reaction. And by stages, I mean like the reactants. And then what do we call the stuff that we make in chemistry? The things we start with are the reactants. Maybe I'll write that here. I got to write up there, but. And if they react, which you'll do a lot of these next year, Stephanie?
Product?
The products. Okay, so we're going to put a line here and say this is nitroglycerin. It's got a really high potential energy. Nitroglycerin. But But remember, they used to move this stuff around frozen, right? So long as I keep it cool, it's not going to do anything but just sit there. Okay? Now I'm gonna warm it up. I'm gonna shake it. Pretend I can do that from far away so I don't get hurt. And I shake it, and by shaking it, I'm giving it, to be honest, more potential energy. So here we go. I shake it, whoa, right up to here. And then right at that point, I've shaken it enough so it breaks apart, and now I can get a big explosion, and I get a lot of other chemicals. And the main chemicals that form, to be honest, are water and CO2. Crazy, after such a complicated explosion. You mainly get two things, water and CO2. And here's where their potential is, those molecules. Oh. So let's just call that the products. And these are the reactants. Well, reactant. I only got one. So what I'm trying to say is, I still gotta add some energy. You know what? I gotta add this much, don't I? And that's the energy needed to make the molecules do what? Local?
React.
React, collide, right? Collide enough to react. On this diagram, that's the activation energy. Ah, so it's the height of like a little hill on this diagram. And my hill is not very big because I don't really need much with nitroglycerin, man. They warm up a little bit, that hill, and then they hit and then they explode. If my products are way down like this, we call this a exothermic reaction. Did I teach you that term this year? Does it ring a bell? Yes, yes, no, no? No, okay, all right. It's not hard as it turns out. Exothermic reactions are reactions that when they occur, give off a lot of energy. Nitroglycerin is a great example, okay? So an exothermic reaction releases energy, often as heat. In the case of nitroglycerin, heat and pressure, change in pressure. I'm thinking of another reaction. It's one that you're familiar with, maybe. No, we did that this year, but that's exothermic too. Let's just do boiling water. Okay, here's my water. So it's liquid water, What are the molecules? What do I got to do with the molecules, Jordan, to make it into a gas? What do I got to do with the molecules? Here they are as a liquid. Heat them up. So what happens before you go is for water, if I boil water, I got to heat them up, and I get something up here which we call steam. So it's not exothermic, it's the opposite, which is called endothermic. And you notice if you cook water on the stove, you got to keep adding heat, right? So it requires heat. Sorry to run you over a few seconds, but that's kind of important. So boiling water, it needs heat to happen, so it's endo. Energy enters in, and the other one, the energy exits. It's a way to think of it. Thank you, everybody. Thank you, folks at home as well. And exactly, Tully, noble gases was right. Okay. Hope you got that, folks at home. See ya. Bye.